I'm Ain Nguyen, and this is my lab report for Lab 3. So the purpose of this experiment is to demonstrate the forces and motion of a mass in circular motion. Uh, and we can examine how information can be derived from the values related to the motion of an object. Using this fact, we can find the mass of a black hole by studying the star's orbit, and then use that information to find the initial velocity of a ship escaping a black hole's orbit. So we use Newton's second law and Newton's law of gravitation, and in the result of this experiment, we found these values. So the momentum principle describes how the net force acting on the system changes the momentum over time. Using the impulse formula, we can rewrite F net as the rate of change in momentum. And here we have the velocity update and position update formulas derived from this fact. So using Newton's universal law of gravitation, objects in the universe all attract each other with a force proportional to the product of masses and inversely proportional to the square of their distances. So we use this formula using the gravitational constant and these values. So since we're interested in finding the mass of an object given the force, we can arrange this equation. Assuming the net force equals the net force of gravity, um, we can say that the mass of the black hole would equal the net force times the square of distance all over the gravitational constant times the other object's mass. So although we don't need this for the calculation of the mass of the black hole, it's important to note that the components of net force acting on the star have different effects. Um, the component of net force parallel to an object's momentum affects the magnitude of momentum. And on the other hand, the component perpendicular to that momentum affects its direction. So in circular motion, this perpendicular component is called the centripetal force. So to calculate the mass of the black hole, we have some initial conditions to start off. We have the system as the star, the surroundings of the black hole, and then we have the time step as 86,400 seconds because we have a 1-day time step. And here we have the star's mass. So here we have the initial conditions, and here we're simply computing the initial and final momentum using mass times velocity, and then calculating the change in velocity and change in momentum using final minus initial. So here we calculate the change in rate of change of momentum so that we can equate it to F net. And using this, we can find the parallel and perpendicular components, which will be helpful in visualizing how the star orbits. And using the formula from before, we can calculate the mass of the black hole using the magnitude of F net. So here we just have the program running, and you can see the perpendicular and parallel components of force here and how that changes as the star orbits. So in our results, we have that the mass of the black hole is about this value, and these are our F net components. So using the black hole mass from part 1, we can create a simulation of a ship leaving the planet orbiting the original black hole. And here we have our initial masses and our system and surroundings. So to simulate this, we have to account for all of the gravitational forces between the planet, ship, and black hole. Here we have just using the law of gravitation, we calculate the position vector and plug everything in. So to update the ships and planet's motion, we can use the velocity and position update formulas. And here are our results. Using our trial and error, we found that the initial velocity could be this value. And we can say that many initial velocities would have worked to let the ship escape the black hole's gravity. So in part 1, the mass of the black hole was average among all of the data points, which may have led to some inaccuracies in the final results of both part 1 and 2. So we can say that the mass of the black hole being calculated inaccurately could have been a source of error. Net force is not different from the rate of change of momentum. Mathematically, it is the same, and the corresponding components of the rate of change of momentum and net force are also equivalent. On the other hand, the rate of change of momentum is much easier to find since it only relies on mass, velocity, and time. So if we wanted our ship to orbit the black hole instead of escape it, we could adjust the initial velocity by lowering the magnitude of the x velocity and increasing the magnitude of the y velocity. And what this would do it would create a more diagonal path initially, which would be more tangent to a circular motion around the black hole. And so Using this idea, I made the initial velocity as -4 times 10 to the 6th and 9.9 times 10 to the 6th. And that is my report.